Okay, so first of all, I would like to thank Wolfram Research to give me once again the opportunity to talk at the technology conference. And what I would like to present to you today concerns several experiments we are doing in our robotics labs. So I'm working in a quite small, we are around 10 people, quite small robotics labs in Sophia, Antipolis. This is south of France. And so I would like to show you some of the experiments we are doing and how we use Wolfram Language in this experiment, and also to discuss how we would like to use more the Wolfram Language in those experiments. Okay, so one of our major center of interest was a few years ago parallel robots. And we were involved in the design and the development on several robots. So parallel robots, you can see we talk about, we said it's parallel robots when the end effector is linked to the fixed base through several kinematical loops. And the opposite is serial robots when there is only one kinematical chain between the end effector and the base. So we have several examples we have developed or designed. This one. Here you can see another one which is used. So this one we do not have developed by ourselves, but we are using it for a walk simulator, for to move the carpet. That's one we have been involved. So it's now an industrial robot for working tools, industrial tools. But we have been involved a lot in the conception of these robots. And maybe an example of a big one we have been involved. So, and at the opposite, an example on a very small one we have developed. And this one has been designed for, I don't know the name, anyway, inside prospection of the body. So it's really, really small. And on the end effector, you can put a very small knife, and then have the surgery can operate through these small robots. So when we are working with such manipulator, we have a lot of equations to solve, a lot of equations to write. So I won't develop a lot of equations. I just want to give you a flavor of that. And that's the first reason why we are using computer algebra system, and when we are using Wolfram Language is for the symbolic computation and the computer algebra features we have in. So here, of course, we are working in three-dimensional with three-dimensional robots, but for the example, I prefer to do something with a two-dimensional. So what is simple with such a robot? This one is a serial. The base is blue, and the end effector is supposed to be the small red arrow. So what is quite simple is if you give the configuration, I mean, if you give the command you send to the motor at each, and you give the angle of each rotation, it's quite easy to find the position. Yeah. So you can see the position is computed directly. What is a little bit more complicated is the inverse computation, because in this case, you have to solve an equation. In the first case, there is nothing to solve, just equation to develop, and it's explicit. In this case, you have to solve, and you have eventually several results. So when you are controlling the robots, such a thing could happen. And when you want to avoid such a thing, you have to locate it very, very precisely. And that's a good reason to use symbolic methods, because when you are using numerical methods, you don't know precisely which solution we will get. So you can follow a solution and then have a jump without really knowing that. Okay, that's why we try to push the symbolic computation as far as possible. But that was quite simple because it was serial robots. If we work with parallel robots, it is much more complicated. So with parallel robots, it is the opposite. What is easy is the inverse one, and what is difficult is the direct one. So if you have the position and the orientation of the end effector, here the end effector is a small red triangle, and the fixed base are the 3 blue rectangles. It's quite easy to compute the length of the legs that link the two platforms. Okay? And if you want to do the opposite, the direct model, it's much more complicated. So, as Bruno showed in a previous talk, I just put a small device to guess the result, and from the guess, try to get the solution. So we can put it here, turn a little bit. Anyway, it's a way to demonstrate that it's very cool to have on the top of a symbolic computation system, to have such manipulation and graphics possibility, and to have everything together, and that's only in the Wolfram language. Okay, it do not compute the model, it's just a way to approximate the solution, as you can see. And if we want to compute it, I told you it's more complicated. So in this case, we are just planar. So we just have to solve some circle equation, but complexity grow very, very quickly. So let's fix some notation, and I develop some computation. So just what I want to show you. So I'm using the same methods as the one I have done by hand. That means I try to eliminate as much as possible all the variables, except the angle. Here the angle appears as a t, which is modulo change of variables, is related to the cosine and the sine of the orientation of the platform. So I first try to solve, to get a polynomial equation in this t that gives me the orientation, and once I have the orientation, I can compute the x and the y. So what is important here is this number. It's 14,600 terms. So that means that is quite big polynomial, and that it will be quite difficult to solve. And we are in the case, in the two-dimensional case, we are only interested for the experiment in the 6-dimensional case. Solving the direct model of such a robot has been made for the first time, I think symbolically, around between 90 and 95. And it has been made with a lot of Grosvenor basis computation. And the result, the method is a little bit similar to that, so a lot of elimination, and then to find at the end only one polynomials. And each root of the polynomial will produce a solution. So maximum, the size of the degree of the polynomial is 40, so that means we can have 40 solutions. And fortunately, usually we do not have 40 real solutions. We have only a few solutions, but we can have 40. So that means that first we need to have good tools to do symbolic computation, and also we need to have good tools to do numerical evaluation of this computation. But what we are interested in is to get the numerical result, and with such high degree, the computation can be very unstable. So we have to perform certified computation, either increasing the precision or using interval methods and interval analysis. So we did both, and we are doing both. And we are doing both with the Wolfram language, because those functionalities are available in the Wolfram language. More recently, we have been interested to cable-driven cable-driven parallel robots, because once the solution of the model has been found in the 80s, in the 90s, okay, the researcher wanted to find another game to play with, and so it could be the same, but it's even more complicated for two reasons. The first reason is that on a cable you cannot push, you can just pull, yeah, thank you. And so you need to have more cable to ensure that you can move in all directions. So maybe I can move a little bit so you can see all the cables are attached to the cube. So it's a quite common configuration. And by changing the length of the cable, you will move the cube, and you will get it to move in the with 6 degrees of freedom. Of course, with small courses, due mainly to cable intersection, but you have 6 degrees of freedom, provided you have at least 7 cables. And the second reason why it's much more difficult to compute, it's because you cannot use just the geometrical or kinematical model. You need to take in account the force exerted inside the cable, because you need to know when a cable is no longer straight. Yeah, thank you. And so it's important because at this time some dimension changes and the computation change. So you need to use a statical dynamical model. So that's why we need a tool which is good not only for symbolic computation but also for numerical computation, because we have no hope today to get a symbolic result with this geometrical and statical model. Okay, so I will show you a couple of experiments we have done. So we first have a rescue crane. So we have 6 devices like this one with one cable, and we put one of the top of several of the top of the battlements, and the idea was to control this part of plane as something to rescue people mainly, and maybe. So here is a view of the ensemble with 5 of the 6 devices. The 6th one is a little bit below on the parking lot there. And with the help of numerical computation of the model and control, we can almost safely move the guy who lies on the platform. And we can also use these things to try to escape a guy or remove some object without taking any risk. So that was one of the experiments we have done. And we also have a series of smaller robots, which name is Marionette because it's moved by cable. So this one is the first one. It is a cuboid of let's say 2 by 1.5 meter, maybe 2.5 by 1.5, and we have 8 engines. So on this picture, only 4 cables are in effect, but it is linear engine. You see one here, and we have 8 linear engine on this robot. Okay, another example is a crane to move people in a room. Yeah, for example, for disabled people or tetraplegic people. So this one, there is still 4 cables, and in this case, we do not have to control rotation. So with 4 cables, it's completely enough, and the 4 cables are attached at the same point. And the last one, it is a robot we have installed in a virtual reality room. So we have a wall of screen, and right now we have done just very small experiment, but we would like to experiment the mixing of virtual reality and this kind of technology, of robotics technology. Okay, so that's it for the main part of the of what we call robots usually. But those days robots are much more complicated, and we call robots whatever kind of complex system which can sense the environment and take some decision and react on its environment. So the lab probably progressively has shifted to assistance robotics, and we are dealing with devices and connected devices. And the problem begins to be different. We are not that much interested in the mechanical or geometrical models. We are much more interested in communication, in data acquisition, and data analysis, modeling, control, and so on. So a few examples. Okay, one more crane. It has been designed for the European Robotics Weeks. The idea was that it's supposed to be a nuclear plant with something burning, and we have to put this moving stuff in the red box. And it was supposed to be a game during these weeks. So we have to control this device from a website, in a kind of website. So at this time, we had not enough access to the Wolfram language, so we have made that with another language for dealing with devices and connected device, which name is OP. But I would like to set up again this experiment with the Wolfram language as soon as it will be possible. So what I have done with the Wolfram language is some kind of simulation, and you can move the end effector as you want, and then you can see what you can see here are the commands computed by the models. And if you check that, then you send these commands to the device. The device there are fidgets. It's not Arduino equipped, so it's fidgets. Fidgets are a little bit like Arduino series, but it is made by Sun Microsystems. And I would love Wolfram to consider that using this device in their program. And with this, to attack this fidget, we are using a JLink and the Java API. So that's what is done. And we would like to implement some Raspberry Pi based solution, but the test we have made with the Raspberry Pi is that it's quite low, especially if you want to do some graphics. So I will have no problem to compute the model and to send the order and to make the control loop. But I'm afraid I won't be able to have this interface working on the Raspberry Pi. Okay, we also did some calibration and auto calibration through image analysis with the help of Wolfram language. What else? So we are working with Rollators, and we did some some experiments. So this one was a medical experiment. We wanted to enhance the usual medical test for walk, and this test is usually, at least in France, is usually your doctor is just controlling how much time you need to go there and come back, and the only measurable quantity is the time. And with such a rollator, which is equipped with a sensor on the wheels and 3 accelerometers, with such a rollator, we can have a good idea of what is the trajectory. So we use Wolfram language to, once we have got the result, we have got the result with other devices, but when we have got the result, we use the Wolfram language to analyze the devices, and that's the result of one experience. We get the trajectory. And that's the result we had with several people working. And here, we had two sets of people, and one set was quite old people, and the results are in blue, and the other set is in red. It was quite young people. So we can see from here that there is something to analyze there, and we are currently working on, on that. So with this rollator, which is a little bit more big and more equipped, so this one has motors and brake on the wheels, and also that's a solar panel to get for the energy, and there is a PC embarked and several accelerometers, the GPS and so on. So with this one, we walk through the campus, and we have find the place, the different the stiffness of the road, stiffness of the road, and anyway, yeah, it's better I show you. So that's the campus, and so the green line are the place where you can easily walk. It's quite flat. The blue line is a little bit like that, and the red line, it's not possible to go with a wheelchair, for example. And also each of the KB, it's the place where the sidewalk is doing like that, so you can go with a wheelchair. Yeah. So all that stuff I've been done with the help of this rollator, and we use the Wolfram language to get the results and to analyze the result. I mean, especially change the format of the result to be able to export it to OpenStreetMap project. Okay, one more example. So it's a small robot, so it's a toy we use for one-week internship program for 13 to 14 years old students. And the idea is to make those people understand all the problems which are behind using a robot, the control, calibration, and modeling, and so on. And of course, the robots usually come with manual commands, and we change that with a fidget board. So they also have to understand the board and how it works. And we control all that things with a Wolfram language program. So I will show you what kind of things we have. It's a bit bigger, a bit big. Oh. Okay, so that's the kind of thing I ask them to build, to draw this simulation. And what we are doing with the Wolfram language on top of this model is to do a high-level task to try to understand how the high-level task can be divided into low-level tasks. And also we realize a fidget connection, and we can connect the computer to the robots. What is not yet done is to connect this kind of interface, just moving the interface, and then the robot is moving. It's not yet done, but I think we could do that soon. Okay, so the last example, we change the legs of a bed. We replace the legs by 4 sensors, and those 4 sensors are connected to a Raspberry Pi. So the Raspberry Pi is connecting the data of the 4 legs of the bed, and we have some records for 1 night of sleeping, of course. And so from this data, we try to guess what are the phases of sleeping, and we are experimenting with doctors. We are experimenting how they can use that to replace the heavy process of experimenting measurement of sleep. You know, it's something very heavy. You have to put EEG and things like that. Okay, so and we also would like to see how it is connected to the small devices we could have, for example, the Nike things you put there, or the Fitbit, or things like that, activity trackers. And that gives also results concerning how you sleep. So what we got is, yeah, that's the mass versus the time. Here we have the mass center position, and we try to guess the motion of the people inside the bed. And after some analysis, we have some result on the sleep phases analysis. So each color means one of the sensor, and you can see that we have concordance of the result. We are still working on this study. Okay, I think it's time to conclude. So the reason why I like Wolfram Language is because it's doing all the things, and everything is really integrated. I mean, it is always the same idea, the same way of processing whatever you are processing. You are processing images, sounds, polynomials, numbers,